Okay, 6.4, exponential growth and decay. Starting off with exponential growth. An exponential growth function has the form y equals ab to the x, where a is positive, b is greater than 1. And over here we have our formula. This should be a 1 plus r. The r is the growth factor, or the whole piece is the growth factor. The r is the rate of growth, right? How fast it's growing. If something says that it's growing at 10%, you first need to convert that into a decimal. That would be 0.1. And then in this formula, you'd have 1 plus 0.1 in the parentheses there, right? So the rate of growth would be 0.1. The growth factor would be 1.1. Exponential decay is when a quantity decreases by the same factor over equal intervals, right? Exponential growth, you multiply by the same thing each time. Exponential decay, you decrease at the same rate each time. Here it is still written as y equals ab to the x, where a is positive. This time b has to be less than 1. If we're looking here, it has the 1 minus r. Again, if we say that it's 10%, this time it's decreasing by 10%, which is 0.1. So here in our parentheses, we'd have 1 minus 0.1, which is 0.9, right? This is another way to say 90%. So saying that something decreases by 10% each time, you could reword that and say that it is 90% of what it was, right? There's a 10% loss. It is 90% of what it was. All right, looking at example 29 here. We're going to decide if it's growth, decay, or neither, and it has to be exponential growth. Looking from 5 to 20, that multiplies by 4. 20 to 80, multiplying by 4. And then 80 to 320 is also multiplying by 4. Because all of these are multiplying by 4, this will be exponential growth. Example 30. 960 divided by 4 is 240. On each of these, we could divide by 4. Another way to think of that, because right, exponentials we normally multiply, would be like multiplying by 1/4. All right, so that would be what we would really be doing. We're not really dividing by 4, we're multiplying by 1/4. That's the way to think about that. So this is decay, and it's exponential because they're multiplying, so this is exponential decay. All right, example 31. We're supposed to determine whether the function represents exponential growth, decay, or neither. This is supposed to be y equals 3, parenthesis 1.15 to the x. Whenever you're deciding if it is growth or decay, the only thing, let's scroll back up here. The only thing that changes is that here b is greater than 1, here b is between 0 and 1. That's the only thing that you need to look at, the only thing. Where were we? Right here. Here we look right there, b is greater than 1, right? 1.15 is larger than 1, so this is growth. This would be, if you wanted to think about it, this would be a 15% increase, right? 1.15 would be a 15% increase. Next up, this is supposed to be y equals 7, parenthesis 0.94 to the t. We look right there, that is less than 1, so this is a decrease, this is a decay. This would be a 6% decay because 1 minus 0.06 gives me 0.94, and 0.6, this guy right here, is 6%. Example 33. This should read as y equals 10, parenthesis 1.5 to the t over 4. Now, it says to rewrite the function. We do not have to do that. You don't need to rewrite them. If on the book, on the homework assignment, if it says to rewrite, don't rewrite it. Just look at this. We still have the 1.5. That is greater than 1. So this is a growth. Right? Exponential growth. Example 34. This should be y equals 0.7 to the t minus 2. This one's going to be decay. Right? And the purpose of problems like this is to look at the exponent changes here, right? It's a little bit different. It's still growth and it's still decay, right? The growth and decay is still determined by whatever's in the parentheses there. Example 35. This should read y equals 5, parentheses 0.65 to the t plus 8, right? We don't care about the t plus 8, right? That's interesting. That's different than what it normally is. We care about the 0.65. This is decay. All right, next up, compound interest. This is a good thing to write down, and I'd suggest writing all of it down. So if you need to pause the video, you should do that. And, well, I'll continue now. We've got y equals p, parenthesis 1 plus r over n, all to the nt. P is the principal amount, however much you deposit into the savings account or whatever it is. And then in parentheses, we have 1 plus r over n. A lot of times things are listed as an annual interest rate, right? If you have a savings account, you probably see an annual interest rate on that. They take the annual interest rate divided by the number of times interest is compounded, right? A lot of the times, savings accounts will compound interest monthly, right? If you look at your savings account, a lot of the time, there will be every month, right around the same time of the month, there'll be a deposit for however much interest you had, right? And that's saying that the bank calculated interest at that time and deposited things into your account or deposited money into your account. So in the savings account scenario, the N would be 12 because there's 12 months in a year, right? If it said it was compounded weekly, then it would be 52. If it was daily, then it would be 365. So normally, let's compare this to y equals ab to the x, right? We want to compare it to that. A would be like our y-intercept. That would be our initial value. That's P, our principal, right? If we're talking about savings accounts, then the principal is however much you deposit initially. B is what you multiply by each time. It's how fast it grows. So in this scenario, it's going to be 1 plus, because it's going to be exponential growth, right? Exponential growth has a plus there. And then we take the percent divided by the number of times it's compounded a year. And then we multiply by, or we have the exponent n times t. That's the number of times compounded times t years. So if this was a savings account, it might look something like y equals p, parenthesis, I don't know, 1.0012 to the 12t. It might look something like that. And this is a small decimal, right? It's 1 point and then there's a few zeros, right? Because savings accounts don't have a lot of interest on them. They don't have a high interest rate. All right, let's look at example 36, and maybe this will start to make more sense. You deposit $300 into an investment account that earns 3% annual interest compounded monthly. You have a savings account with a constant balance of $100. All right, so we have two different accounts. The first account we put $300 in, and it generates interest. The second account does not generate interest, right? It would be the same thing as taking a $100 bill and putting it under your bed, right? There's no interest, there's no change, it stays the same. Part A, write a function M that represents the balance of the investment account after T years. Well, we need to look at part A here and find some things. Our principal is how much we put in initially. That's going to be 300. My rate is 3%, or written as a decimal would be 0.03. N would be 12 because it's compounded monthly. Now I can write M of T. Right, M of T is going to be my investment account. P is 300, parenthesis 1 plus my R over N, so this would be 0.03 over 12 to the 12T. Now we want to simplify this a little bit. We'd have M of T equals 300. And then this should be 1.0025 to the 12T. So now that we have this formula, we could look out and say, well, how much money would we have in the investment account in 5 years? Right. Part B, write a function B that represents the total balance of the two accounts after T years. Then find and interpret B of 5. So for part B here, B of T is going to combine both accounts. Well, we already have M of T, so this would be M of T, and then we have to add the other account. The other account is at a constant balance of $100. Rewriting this to be a little bit nicer, I'm going to plug in for M of T, this is 300, parenthesis 1.0025 to the 12T plus 100. So there's my formula B of T. Now we need to plug in 5. If we plug in B of 5, we have 300, 1.0025 to the 12 times 5 plus 100. If we type all of that in, we should get 448.49. All right. Let us scroll on. Example 37. This one has exponential decay. So the value of a car is $15,000. It loses 10% of its value each year. We're going to write a function that represents the value y of the car after t years. Then we're going to find the approximate monthly percent decrease in value. And then we're going to estimate the value of the car after 8 years. So starting off, let's write a function. Part A. Our function is going to be y. We'll just call it y of t. That makes it a little bit prettier. My initial value would be like my principal. That would be 15,000. Now, instead of 1 plus, I'm going to do 1 minus because it loses value. This is going to be my rate, which is 0.1 over how many times does it compound each year? Oh, this is just a full year. So I can just say 0.1 to the t. So simplifying this a little bit, y of t would be 15,000 times 0.9 to the t. Part B, find the approximate monthly percent decrease in value. Well, it decreases 0.1 over the year. So if we divide that by 12, that gives me 0.0083, repeating, which is 0.83, repeating, percent. All right, so the car would lose 0.83% of its value every month. Part C, they just want us to plug in 8 to the function in part A. So this would be 15,000 times 0.9 to the 8, which should be about 6,457.008, and we'll round that to the nearest penny. So this will be 6457.01. Alrighty. So that was exponential decay, and that was talking about the value of a car. Up here, this was exponential growth. There will be more problems like this, so make sure you know how to do this problem specifically. it would be a good idea to have the compound interest formula written down somewhere. All right, that's all.